Good morning to everybody. Welcome to the mass transfer course. Today will be lecture 11. And we are discussing about the convective mass transfer and mass transfer coefficients. In lecture 9, we have understood the different types of mass transfer coefficients and their expressions, and how, if one mass transfer coefficient is known to me, then how can I convert this one into other with this conversion. And lecture 10, we have solved 3 problems to understand this thing in better way. Today we will talk more about the mass transfer coefficients, because last day we told you can calculate the mass transfer coefficients if you see our problem, there are problem number 2 and problem number 3 was there. Here we saw in one case the film thickness delta was given and we have calculated the flux and mass transfer coefficient. And problem 3, flux was given, then we calculated film thickness delta and mass transfer coefficient. But in reality, what is the film thickness delta and flux, both will be unknown. And we told that mass transfer coefficient is closely related with the delta. If delta is low, then mass transfer coefficient will be high. And accurate determination of mass delta is very tough job. Already you have experienced this in your heat transfer course. Just I am going to little bit review of this one because it is very similar, mass transfer coefficient and heat transfer coefficient. So here I have taken one hot surface here, okay, and what the fluid is flowing, let's assume there is a fluid film thickness delta, okay, and that is stagnant fluid, let's assume. So here the hot temperature Ts and bulk fluid temperature is T0. So heat transfer happening from higher temperature to lower temperature, but let's assume this film, this is stagnant film. Then if this is a stagnant film, then I can use this equation, Qx flux and minus K, okay, into T0 minus Ts, T0 minus Ts, I started from this minus this, divided by the thickness delta minus 0. So delta, this is minus 0. So then if you take, because this is lower, this is higher, so I take this Ts minus T0, then the negative side K by delta. And my, that is K by delta, that is equal to my heat transfer coefficient. See, K is the property of the fluid, thermal conductivity, it is known. But to calculate the heat transfer coefficient, the delta has to be calculated, and this is the problem generally. And in problem we have seen the delta thickness is in millimeter, 1 millimeter, 2 millimeter range. An accurate determination of delta for a turbulent flow, it is very difficult, and till now no theories are developed. and that is the problem. Similarly, for mass transfer also, if you see that k dash c, k prime c, that's mean diffusion, equimolar counter diffusion. Okay, where concentration, molar concentration is the driving force, that is also then it is coming that here k by delta, here it is coming dAB by diffusivity by delta. It is thermal conductivity by delta in case of heat transfer, and this is again for this is for gas phase equimolar counter diffusion, whose concentration difference is in terms of molar concentration. For liquid phase KLS, that is the mass transfer coefficient in liquid phase. For prime means equimolar counter diffusion, and that is if molar concentration is the driving force, then dAB by delta. In both cases, so it is very similar, mass transfer coefficient and heat transfer coefficient. If you see, dAB will be known to you. Generally, for a particular system AB, it is known. Okay. If you did the experiment and it is reported in literature, you will get this value. Okay, but for a particular system, what will be the delta? It will keep changing, because if you increase the velocity, delta will decrease. So what is the delta determination? That is very tough job, and because of, and still now no theories are developed. And this is the problem. See, master heat transfer coefficient and mass transfer are very similar, and in both cases determination of heat transfer coefficient, master problem is accurate determination of. Now last day we have taken, so if you see that Kc dash dAB by delta and KL dash this is delta. See, for other mass transfer coefficients, okay, the conversion factors are there, okay, but no, all these, but everywhere if you see, if you take the any mass transfer coefficient, everywhere dAB by delta is there. dAB by delta, dAB by delta, dAB by delta, everywhere it is there. This is a fundamental thing. With this, there is some conversion factor. And what is this conversion factor? What are the things? Generally, that for gas phase PRT, okay, sometimes if it is a diffusion through A not through non-diffusing B, then that PBM is coming, log mean, because it here concentration profile is not linear. So that conversion factor is coming, and that is very easy to determine. It is very easy, you can get it. So fundamental things, if you, let's take, if you have this one, so accordingly you can convert the other things. So here thing, that's why if you see this case dAB by delta, dAB by delta, this is the fundamental. If you know this thing, the other can be converted. Now, to know the mass transfer coefficient, so you have to determine the delta. That is the plane thickness. Because in convecting, mass transfer is occurring when fluid is under motion. When fluid is under motion, so it will form one boundary layer with its wall, and because of this thing, the mass transfer. Now, how will you determine this delta? That is one challenge. And how do we deal with in heat transfer? Because we cannot, if you see, there was no theory in turbulent flow where you have calculated the heat transfer coefficient through with some theories. For laminar flow it is possible, but for turbulent flow no theories are there. So this is one gap. You can do research or not, but if you can solve this, see, this is not solved still, till now, 21st century. If you can solve this problem, your name will be written in the book. But someone would manage this one to calculate because that is required for engineering. Engineering approach is, you should understand the difference between engineering approach and approach of science people. Science, okay, physics, mathematics, they need the accurate result. 100 per no deviation they will know, but for that time if it takes 100 years to solve this one, they don't have any issue. But for engineers it is not like this, because we have to solve this problem with acceptable. Means I don't need 100% accuracy, but if it is accuracy is 95%, it is acceptable, but I need the quick solution. So that's why engineers came with a solution to calculate the either heat transfer coefficient or mass transfer. So how do we calculate the heat transfer? So here if you can understand, we calculate the heat transfer coefficient with detached voltage equation, famous. And detached voltage equation, if you see, there are three dimensionless number. One is Reynolds number, Reynolds number, and Masson number. That is the simplest equation. There are some other equations are also there, complex, but this is the so the people use some correlation with dimensionless. Now today we'll talk about the dimensionless numbers and how, and using these dimensionless numbers, how can we calculate the mass transfer. So if you go the dimensionless number, the first number already you have studied in fluid dynamics and your heat transfer, that is the Reynolds number. Reynolds number means it is a ratio of two forces, that is inertial force by viscous force. So when in a pipe fluid is flowing, what is the inertial force? Because fluid has a velocity, so that because of that inertia, that fluid will try to carry the in this case inertial force can be two types, that is dynamic inertia and static inertia. But in the case of fluid flow, that is dynamic inertia. And you feel this inertia force very well when you are traveling in a car. Okay. Car is moving, you are also same velocity. Car, if there is a brake, you will go front, you will lean to the front because of your dynamic force. So when fluid is flowing, there is one inertia, so it will try to carry this fluid forward. What is viscous force? Viscous force is trying to resist this flow. Okay. Because of this viscous force is trying to resist this flow. So there is a competition between two forces. Dynamic inertia force is trying to fluid keep forward, and viscous force is trying to resist this flow. And that ratio is called the Reynolds number. And the beauty of the dimensionless number, you can understand. If you take the Reynolds number for pipe flow means geometry is fixed. Okay, that will be pipe, any diameter it can be. And if you take any fluid, you know how many fluids are there, thousands of fluids are there. But if Reynolds number is 2100 up to 2100, the fluid flow will be laminar. If you take any fluid, all and any, the geometry is pipe flow, but if you take any diameter or any metal pipe, that will be up to 2100, the fluid will be under laminar. Then 2100 to 4000, it will be transition region, means it will be some places will be turbulent, some places will be laminar, and some places will be mix of like this. It is some intense. And if it is the Reynolds number is beyond 4000, then it will be turbulent. So you can understand the Reynolds number, this numbers is covering a vast range. If that is only circular pipe, circular geometry, then it can be any diameter, and if you take any fluid, then this is the condition. So that is the beauty of this, because it is the ratio of two type of forces. If Reynolds number high means inertia force, what are that dynamic inertia, that is predominating. And when Reynolds number is less means then my viscous force, which is trying to resist this flow, that is predominating. And you should understand that concept, that dimensionless number. Sometimes people don't try to understand, but you should understand Reynolds number is a very important number. Why? Because only this number, whatever the fluids you will take and whatever diameter you take, only the geometry is circular, then this will be clear. And what is the inertia force? That is rho v square. Force per unit, rho v square, and viscous force mu du by dl, so mu v by l, so I can write this, v will cancel, rho v rho l by mu. But here if you see, where l is the characteristic length, in case of pipe flow it will be diameter of this d. Okay. And rho here if you see, Reynolds number is combination of two things. One is the geometry of this. Geometric properties, length, characteristic length. Okay. And process condition, that is the V, velocity. Velocity you can do. And rho and mu, this is the property of the fluid. Which property you are taking, accordingly rho v will cancel. So this is a very, very important number is being applied in our engineering, chemical engineering subjects. Dimensionless number, where if you see any dimensionless number, dimensionless means there is no dimension, isn't it? And that number has a wide application, it covers a vast range. That's why I tell you that it is covering, if you take any fluid, okay, and if geometry, only the constant in geometry is circular, then you can take any diameter, okay, 5 meter to 1 centimeter, whatever diameter you take, it will be, if Reynolds number is 2100, then up to 2100 it will be laminar, 2100 to 4000 it will be transition, above 4000 it will be turbulent. Okay. Now, although you know, just I am reviewing this thing of heat transfer part, okay, and then how the dimensionless is coming, you should check it. Okay, Reynolds number is inertia force by viscous force, that rho, this is the rho v square by mu by d. Now what is mu dl is tau, tau equal to mu du by d. Sign I am not considering because I can put it there. Now what is tau? Tau is usually force per area. Force per area means, I know Newton's second law, that m into a. M means kg, meter per acceleration, and meter per second is velocity by another second, by second, that will be acceleration. So this is the force and this is the meter square, equal to mu du is meter per second 1 by m. So kg per meter second square, mu 1 into m. So mu equal to kg per meter second. This is the unit of discussion. You know this. Now, how? Just I will cross check how the whether it is dimensionless number or not. Rho v square, rho equal to density of the fluid, kg per meter cube. V equal to m by s square. So this is equal to kg per meter, meters cancel out, meter second square, and mu du dl or mu v by l. Okay, so the kg per meter second, that is the viscosity. V equal to m by s, 1 by l equal to 1 by m, so kg per meter square. So this is the dimension. In every dimension you should calculate this, but in any dimension it is ratio between two same properties. It may be the heat transfer, it may be, here in this case it is the forces, sometimes it will be the heat transfer. Let's see. And let's see the other things we have studied already. You have studied in heat transfer. So that was one Prandtl number we have studied in already. Okay, Prandtl number, what was that? That is Prandtl number. It is the ratio of momentum diffusivity by thermal diffusivity. Momentum diffusivity is nu and thermal diffusivity is alpha. You know this. Mu by rho, that is nu, this is the momentum diffusivity. Thermal diffusivity will k by rho Cp, that is the thermal diffusivity. Then you can make this simplification mu Cp by k. This is my Prandtl. Actually this is the ratio. You should understand the physical meaning of this, momentum diffusivity by thermal diffusivity. So there are, when heat transfer is happening, let's take from hot water. Okay, so there's fluid flow is happening, then that is the momentum diffusivity, and heat transfer is, that is thermal diffusivity. Now if you see the mu Cp by k, this is the property of this fluid. Mu is property of the Cp is thermal conductivity of the heat capacity of the fluid, and k is the thermal conductivity. So Prandtl number is the explicitly the property of the fluid. Okay, so for liquid metal means high thermal conductivity, but low viscosity. So that for the thing, liquid metal has a generally Prandtl number 0.01 to 0.04. Okay, generally this, so liquid metal have a very low Prandtl number, and diatomic gases has generally 0.7 in this. Water at 70 degrees centigrade has 22.5. Why I am telling, sometimes you should understand which component has a low Prandtl number. Then you should understand the liquid metal has, because that it has a low viscosity and high thermal. Steam, saturated steam has 1. Sometimes people will ask question which has the Prandtl number 1, that is saturated steam. Okay, 1. And viscous liquid, in generally viscous was around 6. Now what is the beauty of this? And already you have studied, if Prandtl number is less than unity, less than 1, if Prandtl number is less than 1, that means momentum diffusivity will be lower than the thermal diffusivity. And then you have studied that momentum boundary layer remains within the thermal boundary. That already you have studied in your heat transfer case. Thereafter, another important number was Nusselt number. Nusselt number, if you see, that is also, if you see, this is momentum diffusivity by thermal diffusivity. Both are different. In this case, convective heat flux through the wall, heat flux by conduction for same delta T. Means whatever heat transfer happening for the convective heat transfer, but if this heat transfer occurs by conduction, then what will be? So convective heat flux means total, if you take the H A delta T, okay, heat transfer and area I have taken, this is delta T, and conductive is K by L A into delta T. So it will cancel out HL by K, where L is the. This is the, so HL Nusselt number, if somebody asks you that what is Nusselt number, tell like HL by K. Tell the first physical meaning, convective heat flux through wall divided by heat flux by conduction for same delta. If anybody asks what is this Prandtl number, what is the Reynolds number, what is the, first tell the physical meaning of this. Then you tell that in mathematically it will be H L by K. Okay. Then you have studied your Piclet number. Piclet number is rate of heat transfer by bulk flow, okay, by rate of heat transfer by conduction. This is very important. Bulk flow when one fluid is flowing, okay, because fluid itself has heat capacity, so it will carry also the heat, okay. So that's the heat transfer by bulk flow. When fluid is flowing, it will carry the heat, that is heat transfer by the bulk flow, and then there is a wall, there will be some heat transfer, okay, that is the conduction. So what is the bulk flow? V into rho, m dot mass flow rate into Cp into delta T, okay. So this is your heat carrying by the fluid, okay, by heat transfer, this thing per unit area, and conduction K by L delta T, so it will be cancelled by rho V L Cp by K. This will be the final, but it is the thing is the rate of heat transfer by bulk flow by rate of heat transfer by conduction. Now this thing, the Piclet number, it is the product of Reynolds number into Prandtl number. Reynolds number V rho L by mu, Prandtl mu Cp by K, then this is K. So Piclet number is the product of Reynolds number and Prandtl by Prandtl. Now what is the significance? See, if I know better heat transfer through the wall, so my Piclet number should be low. If fluid carries the heat 1, then the wall through the, because generally heat transfer, hot fluid will be there and cold fluid between one partition. That is what. Now I want heat to be transferred from hot fluid to cold fluid. That is the second heat transfer by the. But if what is hot fluid, it itself carries the heat, then the heat transfer will. So Piclet number should be low, then my heat transfer will be. Then there was another number was Stanton number. Stanton number was the rate of wall heat transfer by convection, rate of heat transfer by bulk flow. So convection is H into delta T, that is the heat transfer rate of convection, and bulk flow just like we told V into rho Cp, that is A V rho by C. And this also it is the product of National number by Reynolds number, that is that. It can be mathematically, it can be proved. Okay. So practically these 5 numbers you have studied. Apart from the another 2 you have studied, that is a Reynolds number. Reynolds number is very much similar to your Piclet number, only this number is important in case of heat transfer in laminar flow in pipes. That is Piclet number into D by L. That is the thing. That is also. And for our natural convection, the Grashof number is very important, isn't it? So Grashof number, what is inertia force into buoyancy force by viscous force square. That is the thing. So inertia force rho v square, buoyancy force rho beta g delta t into L, and viscous force mu v by L square, and finally it will come beta g delta t L q by nu square. Okay, this is the question. So these 7 numbers you have during your heat transfer, and among them 3 numbers were very important. That was Reynolds number, Prandtl number, and National number. And with these 3 numbers, you have calculated your heat transfer coefficient. Okay. Similarly, we have the dimensionless groups in mass transfer. So Reynolds number it will be same for heat transfer and mass transfer, because in heat transfer also fluid is flowing, in mass transfer also fluid is flowing. Okay, so because Reynolds number is the property of fluid, dimension related to your fluid flow. So that is the inertial force by viscous force. So that will be L V rho by mu, where L is the characteristic and it is the analogous same as this. Here we have studied the Prandtl number, that is momentum diffusivity by thermal mu Cp by K. In case of mass transfer, fluid flow will be there, so momentum diffusivity is there, and in case of thermal diffusivity, that will be the molecular diffusivity. Okay, so momentum diffusivity is equal to nu, and molecular diffusivity, that is DAB. Diffusivity here I have denoted as D. Okay, so Smith number is the momentum diffusivity by molecule. Keep it here. Sometimes people will thermal diffusivity by molecule. No. If you understand the concept, then you will not forget, because mass transfer is related to fluid dynamics and mass transfer, not related to the heat transfer. But here, heat transfer is fluid dynamics, that's a momentum diffusivity, and thermal heat transfer. In this case, momentum diffusivity will come on and it will be molecule. So nu by D. Okay. Then Nusselt number, what is convective heat flux by conduction heat flux across the layer of same length. Okay. So in this case, it will be, in case of heat flux, that will be mass flux. Convective mass flux by diffusive mass flux across the layer of thickness L. Same thing. So what will be convective mass flux? The KL into delta C. Okay. And D, that is DAB, diffusivity by L into delta C, that is that fixed law from fixed law. So if it is cancelled, then KL by D. D here, keep it in mind, this is D is diffusivity. So KL is your my mass transfer coefficient, L is characteristic length, and D is your diffusivity. So in this case, HLK, H was heat transfer coefficient, here mass transfer coefficient, here characteristic, here in this thermal conductivity K, in this case diffusivity. Okay. Then Prandtl number for heat, STH means heat transfer, that is convective heat flux by heat flux due to bulk flow. So in this case will be, that is convective mass flux. Convective mass flux, that is K delta C, and flux due to bulk flow in the media, that is V delta C. Okay. V into delta C. So delta C will be cancelled out, so KL by V. Then Prandtl number was heat flux due to bulk flow, conduction flux across the length L. Okay. In this case, only thing will be flux due to bulk flow of the medium by diffusive, that is flux means mass flux. Okay, mass flux due to bulk flow of the medium divided by diffusive mass flux across the layer. See, when it will be conduction here, in this case that will be a molecular diffusion. That you should understand. So bulk flow is V delta C, and that is D by L into delta C. Okay, so delta C, so L by V into diffusivity. That is Coulomb factor JH is Prandtl number into Prandtl number to the power 230. Okay, so equal to Nusselt number into Reynolds number. In this case, JD is Prandtl number mass M into, in case of Prandtl, that will be Smith number whole to the power 2. That is it. Grashof number will be same. Okay, and there is another important number, that is Lewis number. Okay, Lewis number is what? Smith number by Prandtl. So Smith number means momentum diffusivity by thermal, momentum diffusivity by molecular diffusivity divided by momentum diffusivity, thermal diffusivity. So momentum and diffusivity, so this is which number equal to thermal diffusivity by momentum diffusivity. Actually, this is important where heat transfer and mass transfer are taking place simultaneously. We'll talk about this more detail, particularly when we'll talk about humidification, drying, all these things. This number is so which number means you can understand this is the thermal diffusivity varied by molecular diffusivity, and this number is important when that heat transfer and mass transfer are taking place simultaneously. Okay. So concept is very similar. The Reynolds number, fluid flow, it will be both same cases. In this case, Prandtl number, that is Smith number, and Nusselt number, this is Reynolds number. Where here with Nusselt number you have calculated, because I want to calculate the heat transfer coefficient. Here I want to calculate the mass that I will get. Okay, so similarly for other numbers. Okay, so these are the dimensionless number groups, dimensional numbers in mass transfer. Now, how will you thing is we use this equation to determine the mass transfer coefficient. So people have seen within this dimensionless number, mass transfer coefficient can be calculated, and they done through various experiments, and this develops up, and you can understand the heat transfer. Okay, the Nusselt number equal to 0.023, RE to the power 0.9, PRN, heating 4, cooling 0.04. This is the determinant. Okay, that is the thing, and Nusselt number HL by K, that is mean you can calculate the heat transfer coefficient. Similarly, there is a correlation, okay, where we can thus with the Reynolds number, okay, where you can calculate the mass transfer. So, and you always I am telling you, when there is a correlation, there is a constraint. Whatever constraint they will tell, accordingly that correlation is applicable for that range. Let's take for laminar flow through a circular tube. Circular tube and laminar flow means Reynolds number should be less than 2100. Okay, and the geometry is circular tube. If this is the condition, then Reynolds number KL into D by DAB, that is diffusivity, is 1.62 into Reynolds number into Smith number into DL whole to the power 1/3. This is the correlation. So people did the experiment and they developed this one for laminar flow, and for a pipe circular tube, this is the correlation where you can calculate the mass transfer coefficient. Then for turbulent flow through the tube, turbulent flow through means if it is Reynolds number is greater than 4000, and but you cannot go beyond, but they have did explain up to 60,000. So this correlation is valid for up to they have tested, but beyond that what will happen they don't. And they also saw the Smith number, that is 0.6 to 3000. So this is Smith number. If you see, this is the Smith number is the property of this particular fluid, a component, because nu by diffusivity. This is the property of this component or fluid. So they have seen that if Smith number falls under this and Reynolds number this, then it is very much similar to your detached Reynolds number, where KLD by DA 0.023, Reynolds number 0.083, and Smith number to the power 0.03. This equation will be valid. But this is valid turbulent flow through a tube. If it is a flat, then it will be different. We have already noticed same thing, heat transfer and fluid dynamics. And the thing is, whatever fluid you will take, whatever system you will take, that should have a Smith number within this range. If it is less than this, then this equation may not be valuable because it is not tested, because this is the experimental code. Then boundary layer flow over a flat plate, okay, and if Reynolds number is less than and less than 8000, then this equation is valid JD. Okay, so JD, what is this? JD equal to this. That is also Sherwood number is involved. Sherwood number, Reynolds number, and Smith number. So if you have a Sherwood number, means from there you can calculate the mass transfer coefficient. So JD equal to for this, now JD equal to this. Okay, 0.0664 into Reynolds number L to the power 0.05, and JD equal to, if this is Reynolds number is 10 greater than 10 to the power 5 into 10 to the power 5, then this, and keep it in mind this L means characteristic length. Okay, and flow through a weighted wall tower, then if this is the Reynolds number and this is the range of Smith number, then this correlation will be valid. Okay. The gas flow through a packed bed, it is hollow. Then if you see the Reynolds number, it is this range, and where Reynolds number is calculated based on this, where V dash is the superficial velocity. Okay, is the superficial velocity. If it is this one, then this JD equal to 1.17 Reynolds number to the power minus this. Then liquid flow through a packed gas. This is the, if liquid is flowing through that, then Reynolds number, if this is less than 55, then it will be this value. This equation will be valid, and if this is 3, this range, then Sherwood number will be this. So here I have given few correlations just for understanding that already similar concept is already you have studied in heat transfer. Some correlations are available based on their range experiments. So because I have to calculate the mass transfer coefficient, and for mass transfer coefficient we understand that is actually we should calculate the delta, but delta we cannot able, and if you calculate a delta mass transfer coefficient, then you can calculate the delta, no problem, because you know that mass transfer coefficient is expression by delta, you can calculate, but other things are not. Okay, and how will you calculate the here mass transfer coefficient? With these empirical correlations with you dimensionless number. And dimensionless number is very important because it covers the vast range of your system. Just I told that fluid Reynolds number, similarly it has this vast range and it will cover this. So in this chapter, in today's lecture, we tried to understand what is the mass transfer coefficient and what is the problem in calculating mass transfer coefficient, then how do we solve this one with acceptable limits, and we use the empirical correlation based on the dimensionless groups, and we have calculated the mass transfer coefficient. Once you have mass transfer coefficient, that is, then you can calculate the flux very easy. Okay, because Na equal to mass transfer coefficient into that driving force. Okay, now here with this correlation you will calculate one type. Okay, and they will tell what is it is, see here it is KL, they will tell or the KC or this thing will be tell. So accordingly you calculate, then according to what you need. Let's say you have calculated the KC, but you need the K1. So then you can, then you know, see from correlation you can calculate the KC. You cannot calculate KO because correlation given, okay, this is you can calculate KC or gas. Then once you calculate the KC, then but for your problem you know the KO. So you can then convert KC into KO. Similarly, for liquid phase you have calculated let's take KL. Okay. Now you need KX, then you convert this one according to this conversion. And that's why I am telling you have to be smart enough to convert one mass transfer coefficient to another, because when first you are calculating the mass transfer coefficient based on correlation, this is not in your hand, this is based on what they will tell, accordingly you will get. But what you need in a problem, okay, so according from this calculation then you have to convert this, and we understand how to convert this. Okay, so this is all about our mass transfer coefficient and how we will calculate our mass transfer coefficient. Here, although I have presented few, okay, but you know, if you take a particular system and if you want to calculate more, so many correlation will be available in literature, and for this one you have to do some research and you have to do some, those will do research on this, they try to develop this one. But understanding is very important. Okay, thank you for your attention. Have a nice time.